subscribe to our YouTube channel, Joy Learning TV.
You're welcome to the Joy Learning channel, Senior High School R. It's my pleasure to bring you another learning experience with mathematics. I am your elective math facilitator. My name is Danso. This is particularly for my second year students. And even if you are not a second year student, or you don't really like math, I know that you could still learn a thing or two, believe me. Today we shall be considering coordinate geometry. This will be the first of a multiple part series for coordinate geometry. This is the first part. We shall do a second and surely a third. Well, today we shall be considering the straight line. Now, you would recall that you have some experience, I believe, in functions. Remember that topic? Relations, mappings, and functions. Yeah. Those two topics are important, basic to further topics. And by now you should have noticed that we do a lot of things related to functions in mathematics. Today's lesson, we shall be dealing with the straight line, but it begins from something else. What do I hope we achieve together today? By the end of this lesson, I hope and I believe that together we shall be able to locate and manipulate points in the XY Cartesian coordinate. That word Cartesian reminds me of that great man René Descartes, another French mathematician. And you will find lots of French mathematicians in math. Well, take away the very philosophical Greeks, practical Indians and Arabians, and the next block of really very fascinating people you will find in the world of mathematics are the French, the German, and the English mathematicians. Ghanaian mathematicians, we are coming. African mathematicians will be there. So, well, together, we shall, on René Descartes' plane or system of coordinates, be able to locate and manipulate points. The second thing I hope we achieve together is that we shall be able to determine the characteristics of a line segment, because lines are effectively formed by points. And finally, we should be able to interpret the properties of intersecting lines. So you notice two things I'll be dealing with today are points and lines. Let's begin. So let's locate points. So I've taken the liberty of designing my own grid. Yeah, you have your grid sheet, what you call a graph book or graph sheet. But I'm not using a graph sheet. I'm just giving you something that I think we can work with, because most of your questions will not require a graph sheet, but you need a pictorial representation to understand it. Let's do some math. So you have this. And right from the outset, let me encourage you to get yourself a notebook, a pencil or pen, or both. And if you could, put away every distraction as much as possible. And let's do this together. So I have a grid that I have designed. XY plane, Cartesian, René Descartes. And on my y-axis, I have it ranging from -4 on the bottom, all the way to the highest point, +4. Of course, it could go further. And then on the x-axis, on the extreme left, I have from -5 all the way to +5 on the extreme right. All right. With this, I'm trying to locate points. So say I have these 4 points scattered on my grid system. How do I locate them? How do I identify them? By the way, what is a point? A point is supposed to be a unique location in space. It's a unique location in space. A point is not supposed to have a magnitude. So it does not have a magnitude, theoretically speaking. Now, your house is a point. Your school is a point. Where you are seated or standing there is a point, and it is uniquely identified. If you are in Ghana, well, one of the latest things is the Ghana Post GPS addressing system, where it is supposed to uniquely identify positions, houses, shops, streets, by a very unique GPS system, global positioning system. All right, so this system helps you to uniquely identify a place. In Ghana, it has been increased to not just a spot, which could have been possible, but to a finite area, so that every finite area has a unique address. Hopefully, you will not be too small to fit into that space, or too big, rather, to fit into that space. So we have 4 points on our Cartesian, as you can see on your screen. Now, let's begin from the first quadrant, where you have x being positive and y being positive as well. What do you call, how do we locate and uniquely identify that point? We mean this point. How do you identify it? First of all, you will trace from any of the axes of your choice, preferably from the x-axis. If we did, we will have it located that way, and then for the y, it will be that way. You notice those lines, they intersect at the point. The location of that point is the coordinates that we are about to put up. If we call that point A, then it is 2, 4. I suspect you know this already from your basic school and from a few topics you've treated in your class. It's really not different, it's just math. So point A is 2, 4. 2 representing x and 4 for its y component. All right. What about this second one? In the second quadrant. So the second quadrant has x being negative, y positive. So I'm going counterclockwise or anti-clockwise. Again, 2 and negative 4 intersect. But which one is first? If we call that point B, then it is negative 4, 2. So x always starts. Note that, please. It's a common error for students to interchange them. The x part of it must always start. And then let's move downwards, where x is negative and y is negative, the third quadrant. We have it that way. So which one is first? I want you to try writing it before I go on. What would it be? Try. Okay. If you have your answer down, let's call that point C. So what's your point C? 3, 2, 1, 0. The answer is negative 3, negative 4. If you interchange it, please be careful. So x always begins negative 3 and negative 4. Final one. Without going there, let's call it D. Again, try it. Let's see what you have before I even try doing it for you. What do we have? All right. Point D will have those 2 points intersecting, 5 and negative 3. So point D will be 5, negative 3. So we have been able to locate points. Now, there are 2 important sets of points that usually would confuse students. Now, look at those points. They are in blue. The other points were in black. These points are in blue. One of them lies on 4, and the other lies on negative 2. You see them? All right. How do you locate or name the first point, this one? How do you locate or name that point? Remember the trick. X must always start. X must always start. So for the coordinate system, x must begin, then every other thing follows. Because this is Cartesian, xy plane, it will be x and y. You could have x, y, and z, in which case there will be 3 components for the coordinate system. So if the first is x, we have 4. So what will be y? Well, you see this 0 here. It tells you that on the x-axis, and please note this for now and for the future, y is always equal to 0 on the x-axis. So if x is 4, what will y be? Automatically 0. Even if the point were on -5, it would have been -5, 0. If it were 1, the point were here, it would have been 1 and 0. So our point here, P, is 4, 0. What about on the y-axis? What do you call this point, the second point in blue? Well, if x must always start, and this is y being -2, then how do we write it? Well, on the y-axis, another thing to note is that x is equal to 0. That's the reason for the 0 here. So it means this point, we called it, say, Q, will be 0, -2. I hope this is clear enough. So our first job, almost done. We've been able to locate points on the Cartesian. This is very simple and straightforward. If you remember that the first part of the coordinate system must always be x, then y, then z if you had a third coordinate. All right. Note that wherever there are 2 points, there must be a line by a rule. Anywhere, so long as there are 2 points, there must be a line. So a line is effectively the shortest distance between 2 points. However short, it will be a line. When there is a line, a number of things happen. So for example, when there is a line, every line would have a gradient. Every line would have a magnitude, a size, a length. And every line will have a unique address. Yes, we call that the equation of the line. So let me take that again. Wherever there are 2 points, between every 2 points, there will be a line. Standard. When there is a line, a number of things occur. Number one, every line has a gradient or a slope. We'll talk about that in a jiffy. Every line will have a magnitude, or if you like, a length. And every line will have a unique address, if you like, an equation. So every line has a unique equation. No 2 lines have the same equation. They are unique, remember, because points are also unique. All right. Although a number of points will fall on a line, all of those lines, all those points, sorry, on the line will have a unique family name, if you like. So, for example, in your family, if all of you bear the surname Okafo, Bediakon, or Danso, it means everybody in the family will operate by that surname. Well, if you choose to, some people do it differently. But if your culture permits all of you to use the same surname, that's great. So all the points falling on a line will have the same address or the same surname, if you like, although the points are unique in themselves. So let's try investigating beyond the points. Now we have located the points. You can identify the points. All right. Let's check for the magnitude, which is otherwise called the modulus, or the length of a line. So you could be asked to find the magnitude of a line. It will be the same thing as the modulus of the line, or simply put, the length of the line. Any of these 3 words you encounter mean the same. So let's find the length of a line. By simple definition, the length of a line, or the modulus, or the magnitude of a line, is given by the square root of the sum of the squared difference of the corresponding coordinates of the endpoints of the line segment. So many offs, right? Don't bother. Don't try memorizing this. What do we mean simply, mathematically written? We simply mean that if we have a line, AB, and I'll show you the line very shortly, and one end of the line is A, And the coordinate of that point is x subscript 1, y subscript 1. And the other end is b. So we have a and b. And the coordinates of that point, the very point where the line ends, is x subscript 2, y subscript 2. Then that length AB will be equal to the square root of x2 minus x1 squared plus y2 or y subscript 2 minus y subscript 1 all squared. So it is the square root of the sum of the squared difference of corresponding coordinates. Don't commit it to memory. Just remember that x2 minus x1, I'll square it, y2 minus y1, I'll square it. Remember, I'm saying y2 is actually supposed to be y subscript 2 and x subscript 2, etc. But for convenience, let me call it x1, x2. All right. And when I have squared the differences, I sum them, I add them, and whatever I get from that summation, I find the square root. By the way, let me quickly add here that you could have done it as x subscript 1 minus x subscript 2 all squared plus y subscript 1 minus y subscript 2 all squared and then square root. It will produce the same answer. So whether 1 minus 2 or 2 minus 1, either way you will get the same thing. Usually we like to begin 2, 1, 2, 1. But it could have been the other way, and you'll get the length. So let's do a diagram. So given a line segment AB, and the end point A is 3, negative 2, and the other point is 7, 6. The length will be 7 minus 3, which is 2 minus 1 for x and x, then 6 minus negative 2. I have introduced negative there deliberately. Please do not write 6 minus 2. It is 6 minus negative 2 because y2 here is negative 2 and not just 2. So we have 7 minus 3 all squared plus 6 minus negative 2 all squared. All of that square root. So we would have 7 minus 3, 4 squared. 6 minus negative 2 will be 6 plus 2, which is 8 squared. 4 squared and 8 squared will give us 16 and 64 respectively. If we sum them, we have the square root of 80. That is the magnitude. And we could reduce that to 4 root 5 units. That is the magnitude, the modulus, or the length of the line AB. Okay, it is not really the line. It is the line segment. Why that word segment? It's because the line itself is infinitely stretching. So we demarcate demarcate the line using 2 different points so that we just get the length of a specific point. For example, if I asked you, what is the length of the roads in your country? Say Ghana. Well, if we went to the Department of Roads, they could give us the exact figure. But really, sometimes you don't need all of that figure. You just need the distance from your house to your school. Maybe from the door of your house to the gate of your school. That would be a segment of all the possible length you could find in the city in which you live. So that is a segment, not the whole line. We need only a part of it, not all of it. Why do we do this? Well, I have just told you, giving you an example. Sometimes you just need to find a certain distance and you want to work with it for a different reason. So that is how to find the length, the magnitude, or the modulus of a line. Find the differences between the corresponding coordinates, x, x, y, y, square the difference, sum that squared difference, and then find the square root. All right. The other property is the gradient of the line. What do we mean by the gradient of the line? It's also called the slope of the line. Have you ever tried walking up a mountain before? Well, I live in a mountainous region, so we climb lots of mountains. But well, maybe you don't live in a mountainous region, but have you ever climbed up a staircase? Yeah. When you climb up a staircase, especially if the building is a very high-rise one, maybe 12 stories, 18 stories, and you decided not to use the elevator or the lift, and you decided to use the stairs. By the 6th, 7th flight of steps, you start to feel tired, right? Naturally, except you are very athletic, in which case it's fun for you, you run up it and all of that. Well, have you observed, if you're used to climbing stairs, that certain staircases are easier to climb than others? Yeah. Why? Well, we shall explain it mathematically. Well, or maybe you've traveled in a car or on a bicycle up a hilly place. Do you realize that when you're descending, it's fun? You have lots of wind blowing behind you, or maybe even ahead of you. But when you're climbing, it's arduous, it's difficult. Why? The simple reason is there is a gradient. There is a ratio between your rising and your forward movement. So, we say that the gradient of any line is the ratio, a comparison of the difference in its y coordinate. And remember, y is up, to the difference between its x coordinate, and the x is horizontal. So it's a ratio of differences, difference between the y's. So if I moved from 3 to 5, there's a difference, which is 2. And by moving upwards, I'm also moving horizontally, effectively. So we have a situation where our very popular line segment AB, endpoints x1, y1, x2, y2, A and B respectively. For this, our gradient, which we would call M, and it is our functional notation for gradient M, is given by y subscript 2 minus y subscript 1 divided by x subscript 2 minus x subscript 1. This is equivalent to saying your rise divided by your run. Rise on run. But in trigonometry, or trigonometrically speaking, this would be the same as saying the tangent of theta. And in this case, theta will be the angle between the line and the horizontal or x-axis. It's important to note these three equivalent definitions because from time to time it will be used interchangeably. So your gradient is change in y divided by change in x. The same thing as your rise divided by your run, and the same thing as the tangent of theta, where theta, could have been any other thing, is the angle between the line and the horizontal axis. I hope you get that right. Once again, like in the previous case, y subscript 2 minus y subscript 1 could have simply been written as y subscript 1, or otherwise written as y subscript 1 minus y subscript 2 divided by x subscript 1 minus s subscript 2. So it could be 2 minus 1 or 1 minus 2. However, if you're using subscript 1 minus subscript 2 for y, please do not come to the denominator and write 2 minus 1. No, it has to be consistent. So 2, 2, 1, 1, 1, 1, 2, 2. If you interchange it, you would have a problem. So it's often a good practice to label the question while you solve them to keep in tune with them until you get very familiar with it. So let's try an example. So we have those same points, 3, -2 for A, 7, 6 for B. Let's find the gradient. The gradient will give us, here I am choosing this as y2, x2. And I'm choosing this x1, y subscript 1. So if I say it y2 minus y1, it will be 6 minus -2 divided by x subscript 2, 7, minus x subscript 1, 3. If I switched it, it would have been -2 minus 6 and 3 minus 7. If I use the first case, 6 minus -2, I get 8. And 7 minus 3, I get 4. But if I switched it, I'll have -2 minus 6, which will be -8, and 3 minus 7, which will be -4. In either case, 8 divided by 4 or -8 divided by -4, I'll have my gradient m being equal to 2. So change in y on change in x, that ratio will be 2:1. So I climb twice, I move horizontally once. So if I climb 2 meters up, it means I have moved 1 meter to the right. So that is my gradient. Now it tells how steep or otherwise any accent may be. 2 is quite steep. So 45 is between 0 and 90. So it's halfway between vertical and horizontal. The steeper a slope is, the more difficult it is to climb. If it is, say, 20 degrees, 18, then it is very gentle. So for ramps where our brothers who are physically challenged, using a wheelchair or something, the ramp has to be less than 45 so that it's easier to move on. They ascend and descend on it without needing assistance or a lot of effort. And that's the beauty of mathematics. So our gradient m equals 2. This means that, remember, our gradient m is the same thing as tan theta. So tan theta is equal to 2. That's what it means. But remember, we don't often need tan theta. Sometimes we just want to know what theta is. That is the angle between, say, the staircase and the floor. And in this case, it will be the tan inverse of 2, which will give us approximately 63.43 degrees. Quite steep. Quite steep. Almost standing. All right. So that is our gradient. So we've been able to locate points. We've been able to tell the magnitude of a line segment or modulus or length of a line segment. And now we've been able to tell the ratio between the rise and the run, or the gradient of a line. If you just tuned in, this is your senior high school R on your Joy Learning channel. We have been considering coordinate geometry, the first of a multiple part series, and I am your facilitator, Danso. We are proceeding from this point and we are investigating other things. So, what are the other things you're going to investigate? You're welcome. You're welcome, by the way, if you just joined us. You have missed a bit, but we can go on with you. So, let's investigate for the slope. So, here is a pictorial representation. AB, you notice, is part of a line that is really long and stretching. But we just need between A and B, which is a line segment. All right. So, our gradient M is, as we said, y2 minus y1 divided by x2 minus x1. And we said that it is the same thing as tan of that angle. The angle between the red line, which is the line we're really considering, and the x-axis. It could have been above the x-axis, it could have been below. But all we want is that angle between the line and the x-axis. So if we find the tangent of that, it will be the same thing as y2 minus y1 divided by x2 minus x1. So that is our slope. But we have different slopes. So far you notice that our slopes, our lines, the red ones you can see on your screen, they move from bottom left to top right. So it is rising, like a forward slash. Okay, but we have other slopes. So take a look at this. This is the one you are used to. For this, the slope is positive. the gradient is positive because it is rising, it's positive. We could have the reverse of it, where it is moving from top left to bottom right. It will look like this. Something like this. You see that? So it's like the flip of that. And this time around, it is falling. From this point, it's falling down. Here, it was rising up. Because it is falling, like when you're crestfallen, or you fall to the ground, I hope you don't, it's a negative. So the gradient will be negative. All right, but there are others, two others, and I would like you to guess. So if you had this, and you had this, the one to your left, what would be the gradient? The one to your right, what would be the gradient? Well, if you remember the definition of a gradient, we said difference in y on difference in x, or rise on run. You would realize that for the one to your left, the graph to your left, there will be no change in y because y is the same throughout. Well, if there is no change, that is 0. If there was a change in x and there are changes in x, because a point here, for example, say 2, if there's another point here, say 7, there'll be a difference. The difference will be 5. But for y, if y was 4, it is 4 throughout. So there'll be no difference. So it will be 0 on 5. 0 on 5 is effectively 0. So for any line parallel to the x-axis, if the x-axis is the way we have drawn it, then the gradient of that line will be 0. There's no gradient. It's just a flat surface. No gradient. And that's quite cool to walk on, right? No stress. Just plain ground, flat. A football field ought to have a gradient 0. If it slopes, that would be a disadvantage to one team. It will mean that the team on the higher level could just play the ball and without effort it will move. On a billiard board, snooker board, table tennis table, the gradient ought to be 0. Else, it will mean that if it was a billiard board, you don't need to apply too much effort and all your balls will roll, either in favor or against you, depending on what part of the game you are on. That would not be fair. So, for fairness, the gradient ought to be 0 on a billiard board, on a football pitch. For Tiger Woods, he doesn't need a 0. Indeed, sometimes on such a park or place to play that game, what's that game called? Yeah, what Tiger Woods plays. That will require some slope because he would need to strike and hope that gravity will help him push into that golf hole. Yeah. Well, the second graph, you would notice that we could have different values of y. So y could be 4 at this point, y could be 1 at this point, but here 3. X does not change. So there's a change in y, 4 minus 1, 3, but there is no change in x. So it's 0. So you have 3 divided by 0 because no change. Remember, we're not dividing by 3, we're dividing by the change. But there was no change in x. So 3 divided by 0, you will find out that it will be really infinite or undefined. So for a line that does not change in its horizontal, or if you like, the x-axis, the line has a gradient that is infinite. It means it is perfectly straight. And I hear that chairs in the library ought to have such an orientation so that you do not slip. Well, if the chair can recline on its own, then that means it makes you relaxed. Well, that's what I hear. So, those are other slopes. We have positive, rising, negative, falling, 0 if it is parallel to the x-axis, and infinite if it is parallel to the y-axis. So parallel to this y-axis. So these are 4 basic slopes you would encounter in all of your mathematics and even science experience. All right. Now that we have dealt with that, let's deal with the unique address of a line. We call that the equation of the line. To find the equation of a line, I guess by now you know how to locate points. I guess you know how to find a line segment or define a line segment. I suppose you can now also tell the magnitude of the line segment. And just a while ago, you learned about determining the slope of a line and the 4 different types of slopes we would have. Now let's go to the family name or the equation of a line. So that is the surname that all the other points can bear. So the equation of a line, 2 things that are important, essential parameters. If you want to find the equation of a line, if a question is put before you and you are required to find the equation of a line, there are 2 things that you must have, else you cannot find the equation of a line. What are those 2 things? 1, you must have a known point and its coordinates. At least 1 point and its coordinates. You must know it. So it's like saying, if I want to find out your family name, I need to just find one of you, the siblings, or the children in the house, or just one member of that family. If I know that one member, I can tell the family name. That is with the assumption that you all have the same family name. And the gradient of the line. So for example, if everybody in your country or your ethnic group are named by what they do. So let's say you all sell or deal with beef. So I could guess by your behavior, which is the gradient, that you must be maybe Kofi Butcher. Or if you all plant rice in your ethnic group and you are named by what you do, maybe you are Ama Rice. Okay, I know you are not Ama Rice, but just as an example, if all you do is maybe you roof houses using thatch, then I can call you Essie Thatcher. Or if you all teach in your family and that's your family trade, then I can call you Quadrant teacher, something like that. You get the idea. So 2 things we need to define a line, the equation of a line. 1, a known point with its coordinates, and the second, the gradient or the behavior of that line. So if I have a line segment AB with its coordinate as given, x1, x2, x1, y1, x2, y2, the equation is given as such. Please note this formula. It is critical. Note it somewhere. And I'll tell you what the y subscript a, x subscript a mean. As for m, you know what it is. So this same equation could be written in some other way, like this. Y minus ya, x minus x subscript a equal to y subscript 2 minus y subscript 1. You know what this is, right? Yeah, that is m, the gradient. We've encountered it a while ago. Now, so what is y subscript a and y x subscript a? What do we mean by them? Well, they are just any points on the line. It could be actually x1, y1, or x2, y2, or any other point apart from those 2. Recall that the point A and B are the ones we have named x1, y1, x2, y2. But there are literally millions of other points between them. So call A as the firstborn or the lastborn, and B, either the firstborn or the lastborn, depending on which one you want. Between them, if it's a family of more than 2 children, then there may be a lot more. Or a family of the first person in the family and the last person to be born to that family. Between them, there will be maybe tens, hundreds, thousands, millions of other people who all belong to that same family. So there are many points between the extreme points of a line, and all of them have the same characteristics. So you could have used any one of them as your x subscript a, y subscript a, any one of them. Let's try an example. So again, we go back to 3, negative 2, 7, 6. What is the equation of this line? Well, we just apply it. Y minus, and this time around, I'm using this as x script a, and I'm using this as my x subscript a. I could have used 7, 6, and I will. So we have y minus negative 2, so it's like saying y minus y subscript a, m multiplying x minus x subscript a. Remember, I have chosen to use x subscript a, y subscript a. If you open your textbooks, you will find other denotations of the same thing. Some will just use y minus y1, x minus x1. We're at liberty, so long as we define what those terms are, you could use anything. All right, if I did this manipulation, I'll have y plus 2 equals, now remember, I know what m is from our previous subsection. We found m to be 2, so I know what m is. If I did not know, I would have found out by saying difference in y's divided by difference in the x components. I'll get 2. So I expand group terms. I have y plus 2 equals 2x minus 6. And if I group the terms properly, I have y equals 2x minus 8. Now, this is correct. But what I have done is to write the equation of the line in the form y equals mx plus c, where m is the gradient and c is what we would call the y-intercept. But I could write it in another form. If I choose to write it in the form ax plus by plus c equal to 0, it means my ax will be 2x, my by will be negative y, and my c will be negative 8, all of that equal to 0. We like to write it in this form for some reasons you'll get to find out. Remember, I have used a as my xaya. I would use b shortly now. And this is what I would have. Practically the same thing. So this time around, instead of minus negative 2, I have minus 6. So this time around, this is my ya, and this is my xa. Again, if I multiply, I introduce my m as 2, I multiply, I get 2x minus 14 on the right. I group the terms, I have 2x minus 14 plus 6 equals to y. So I have the same thing, y equals 2x minus 8. So you notice, same answer. And of course, I can rewrite it in the form ax plus by plus c, and I get the same thing. So it doesn't matter which of the points you pick. So long as the point falls on the line, it will give you the same equation. Remember, they are family members. So that is one quick nugget to put under your sleeve. What is it? That if a point rests on a line and you substitute the coordinates into the equation, you should get the right-hand side of the equation. What do I mean? If I put 7 and 6 into the equation 2x minus y minus 8, I should get 0 on the other side. So 2 by 7, 14. 14 minus 6 is 8. 8 minus 8 should be 0. What about 3 and negative 2? 3 times 2, 6. Minus negative 2, that is 8. Minus 8, 0. So that's a trick. So now we've been able to determine the equation of a line. All right. Now let's divide a line segment. Now that we have a line, we can split the line segment. So if I want to split a line into a ratio, how do I do it? Very quickly. I needed to take note of this. So I have a line, I have my coordinate system, and I have a line. On this line, I have a line segment. My first point A, my second point B. And I want to split the line at a point P. This line segment, I can divide it internally or externally. In a minute, I'll explain that. but I want to divide it in a ratio m:n. Why would I do that? Different reasons. Maybe I want to build something between two towns, and I want it to be closer to a certain town for a certain reason, maybe a factory because the source of raw materials is at a particular town. Then that means the factory should be close to that town, if not in that town. But maybe the market is on the other side. So I want a certain proportion that makes it convenient for raw materials and convenient for marketing. So I could do that calculation. Now, if the point is this point P, as you can see on your screen, then because the point is between the two towns A and B, well, I have divided the line internally. But what if I'm dividing externally? What that would mean is that my point will be outside of the line segment AB, but it will still be on the same line. How do we do that? Maybe you are constructing a road, all right? And you want the road to be a certain size, but you plan that in the future you would love to expand. Then you need to divide the length between the two extremes externally, so that you know that, well, I have money to do only this much, but I will need this more in the future. So you could mark off the future point so that in the future somebody does not encroach on it. Well, some of the smartest way to do that is to use all of the space on the extremes and leave off some at the center, so that when you're ready and you have the money, you can, the part that you've left in the center, you could convert it to the road. A smart way, right? Okay, so your external will look like this. It will mean your point is outside Q, and for the future, your extension will be that blue line there. So that is internal and external division of a line. What is the formula for it? Simple. This way. Your internal point, P, will map to the ratio M multiplied by the coordinate of B plus or minus the ratio N multiplied by the coordinate of A divided by the sum or the difference of the ratio. Why plus or minus? You use plus if it is internal and minus if it is external. So if it was an external point Q, it would have been minus. Now look at the order, M by B, not M by A. Plus or minus N by A. So first with second, second with first. All right. So we would have it look like this. X2, Y2, X1, Y1. You could use this or the expanded form of it. What would be the expanded? Remember, when you're subtracting, M must be greater than N. In other words, your ratio, if it was 3:1, it would be 3 minus 1. It cannot be 1 minus 3. Even if the ratio was 1:3, you have to switch it so that the smaller one is subtracted from the bigger one. That is for external. All right. So if you expanded it, it will look like this. So M multiplied by X2 plus N multiplied by X1. It will give you the X component if you divide it by M plus N. And then M multiplied by Y2 plus N multiplied by Y1 divided by the sum of the ratio will give you the Y component of it. If it was external, then you notice the minus would all appear. So you could take note of these as well. Either you use the component form, so X1, Y1, or multiply it linearly. Any one of them would work. So let's take an example. Internal and external division. So if we're dividing internally the point AB in the ratio 3:2, you will have something like this. 3 by 7 plus 2 times 3, all divided by 3 plus 2, and then 3 by 6 plus 2 multiplied by -2, all divided by 3 plus 2. You will get 3 by 7, 21, 2, 3, 6, 3, 6, 18, 2, -2, -4. 21 plus 6 will give you 27 all on 5. 18 plus negative 4 will give you 14 on 5. So our point internally will be 5.4 and 2.8. You get that point, right? So m multiplied by x2 plus n multiplied by x1. M multiplied by y2 plus n multiplied by x1. All right, y1, I beg your pardon. All right, so if we're dividing the line externally, what would we do? All you do is change the sign from plus to minus. And if you did, the 21 minus 6, 3 minus 2 gives you 1. 3 by 6, 18, the same thing as we did before, only this time around you're subtracting. So we have 15 on 1, 22 on 1, which effectively gives us the external point 15, 22. In both cases, if you substituted the new coordinates into the original equation, the left-hand side should give you the right-hand side. So that is division of a line segment. Remember the formula? Yes, m multiplied by b plus n multiplied by a divided by m plus n. Okay, midpoint of a line segment is a special case of what we have just done. When you divide a line and you want the point to be exactly in the middle, it means it's in the ratio 1:1. So your m is 1, your n is 1. Effectively, you have something like this. So you have point A, point B, and point P, assuming it's at the very center, it will mean that it is half of the sum of corresponding parts. In other words, half of x1 plus x2 and half of y1 plus y2. So for our point AB, given by 3, negative 2, and 7, 6, the central point, the midpoint, will be 3 plus 7 multiplied by half, and negative 2 plus 6 multiplied by half, in which case we'll have 5, 2 as our midpoint. So it's a special case of what we have done, midpoint. Right. So when lines intersect, which is the final thing we'll be dealing with, when lines intersect, what really happens? When lines intersect, at least two things happen. One, they will share a common point. So if two lines intersect, where they meet, there will be a common point. Number two is that angles will be formed at that point of intersection. So let's look at them very quickly. To find the common point, we solve the equation of the lines. Remember? Equation of the lines. We solve them simultaneously. And we can find the angles by using this interesting formula that I will encourage you to take down. Tan theta equals 2 minus m1 divided by 1 plus m subscript 2, m subscript 1. What is m subscript 2, m subscript 1? Remember what our m is? Gradient. It means we have to know the gradients of the lines, where the m2 would have to be greater than m1, or vice versa. Just make sure that the lesser is taken from the greater. That's the trick. Okay, so let's quickly investigate that. So we have two lines, 2x minus y minus 8 equals to 0, and negative x plus y plus 6 equals to 0. And these lines intersect. Two problems to solve. Number one, where do they intersect? The point pxy. What is the true value of that point? And number two, what is the acute angle between the two lines? Because it could be two angles that are not necessarily acute. What do? First case, we'll solve them simultaneously. So we'll write it in the form we can solve simultaneously. If we solve this simultaneously, all we need to do is to add equation 1 to 2. It will eliminate y. So we'll get x as 2, which will make y automatically negative 4. In other words, our point P is 2, negative 4. You can solve simultaneous equations, right? Yep. So you have 2 and negative 4. When you solve these two simultaneously, equation 1 plus equation 2 eliminates y, we get x. You can put x in any of the two equations, you get y as negative 4. So first part solved, easy as that. Second part, all you do is rewrite the equations so that you can find m. In this case, m1 is 2 and m2 is 1. So we just put them into the equation. m2 minus m1, 2 minus 1, divided by 1 plus m2 times m1. That's divided by 1 plus 2. So we have tan theta is equals to 1 on 3. In other words, theta is the tan inverse of 1 on 3, which is approximately 18.43 degrees. So what do you do for the second case? Just find the two gradients. The smaller, take it from the bigger for the numerator, which is what you have at the top here. Then 1 plus the product of the two gradients. The product is 2 times 1, 2 plus 1, 3. And then find the tan inverse of whatever ratio you got there. That gives you what we have. So that's how to find the angle between intersecting lines. Now, lines could be parallel, which means that they do not intersect, or they are perpendicular, which means they intersect, and the angle between them is 90 degrees. As you can see here, two lines, they are parallel, they don't intersect, so their gradients are equal. And two other lines that intersect, and they intersect at 90 degrees, so they are perpendicular, and their product is -1. Since their product is -1, it means you can find one if you know the other. So m1 will be -1 divided by m2, and m2 will be -1 divided by m1. Either way. So we could investigate this also. So this is just a summary of it. That parallel lines have equal gradients, perpendicular lines have the product of their gradient being equal to -1. So you could be asked to determine the equation of a line passing through a point which is parallel to a line, perpendicular to a line. All you need to do is, the line you have been given, find its gradient. If the second line ought to be parallel to it, then that line will have the same gradient. If the second line, which you are supposed to determine, is perpendicular, then the product of the two gradients must be equal to -1. Let's do a quick one here. So if I rewrite, I have my gradient as 2. Now I want to find another line parallel to this line passing through that point. If this is true, then the gradient of the line I'm about to find must also be equal to 2 because they have to be parallel. So I just put them in y minus 5. Remember our equation, y minus y1, okay, or ya equals to 2 multiplied by x minus xa. So this is my ya xa. So I put them here. And if I resolve them carefully, I would have this. And my final answer is y equals 2x plus 1. In other words, this line is parallel to this, but it passes through the point R25. On the other hand, if the line ought to be perpendicular, then the gradient of the new line has to be -1/2. And so the line itself will be y minus 5 equals to the new gradient, -½ multiplied by x minus 2. And again, if we resolve carefully, we find out that we have this line, which is definitely perpendicular to this line and must pass through this point. All too soon, we come to the end of another lesson. You have learned how to locate points in space on René Descartes' Cartesian system. You've been able to determine the length, modulus or length of a line. You've been able to divide that line into segments, or that line segment into ratio. We did 3:2. You've been able to find the midpoint. You've been able to find the gradient of a line. You've been able to tell the different types of slopes, positive, negative, 0, indefinite or infinite. You've been able to find the equation of a line, and you've been able to tell when they are parallel, meaning their gradient m1 must be equal to m2, and when they are perpendicular, meaning that the angle between them has to be 90 degrees. There are many more things we could investigate. In our subsequent lessons, we will deal even further with some of those things. I hope to see you next time. This has been Danso, taking you through elective maths, coordinate geometry 1 on your Joy Learning channel. Thanks for the pleasure of your company. See you again next time. Bye.
Subscribe to our YouTube channel, Joy Learning TV.